So anyways, last time we had done 9.5, which was all of these standard operations on matrices. How to add, subtract, and multiply matrices. There's two types of multiplication. There's multiplication by a scalar, and then there's also multiplication when you have a matrix times another matrix. Okay, and that's going to come up to play here at 9.7 once we get to that. I think. So today what we're going to do is we're going to use matrices to solve systems of linear equations. And there's two different ways to do that. The first is the way in 9.6. Okay. It's called Gauss-Jordan elimination. All right. So let me explain what's going to happen. We're going to have a system of linear equations. Let's take something like 3x plus 4y equals 10, and then 5x minus y equals 9. Something like that. And what we're going to do is we're going to create an augmented matrix. Now, in an augmented matrix, what's going to happen is each equation is going to be its own row. And each variable is going to be its own column. So each equation, a row, each variable is a column. And that last column is going to represent the equal to constant. All right? Last column. Represents so the augmented matrix for this equation, for this system, would be 3, 4 equal to 10, and 5 minus 1, 9. So I just read off the coefficients. Now, it is very important that I have things lined up in columns. So all the X's go first, all the Y's go second, and then the equal to constant is last. A lot of times what you'll see in books is they will put a vertical line, whoops, where the equal sign in each equation is. So if you ever see that notation, where they put a vertical line in the matrix to signify where the equal sign is, that's what that's doing. Okay. I tend to not write that, especially not on the board, but that's what it is. So this matrix can represent a system of linear equations. Now, normally when we solve this system of linear equations, since it's lined up, we probably use elimination. And I take let's say I wanted to eliminate the y's. Well, I take and I multiply top equation by a 1, bottom equation by 4, right? And then add the two equations together. Well, there's a whole process of doing that on these rows. And I'm not going to go through that process by hand because our calculator will do it for us, right? Instead, I'm going to say we're going to use technology to put this augmented matrix into what's called row-reduced echelon form. And the process you use to do that is Gauss-Jordan elimination, right? So we can use technology to put the augmented matrix into row reduced echelon form. From now on, I'm not going to write the whole words. I'm going to write RREF, and that's how it'll show up on the calculator too. Process. Oops. Period. So that process is called the Gauss-Jordan elimination. That you use, if we were doing this by hand, you'd use Gauss-Jordan elimination to put in row-reduced echelon form. Okay. Now, in terms of what row-reduced echelon form is, basically it's going to be this really nice form. In fact, let's just go and use row-reduced echelon form right now. And I'll show you how this is done via our calculator. Is that right? All right. So there we go. Everybody see that? So hopefully we remember from last time. There we go. How to do the matrices, right? Second into this button right here. So we go into the matrix menu and we want to edit. Let's just say A. Now the A that my example was a 2x3 matrix. Had 2 rows and 3 columns. And the coefficients were 3, 4, 10. And then 5, -1, 9. Okay. So now what you do to put this into a row reduced echelon form is you go to the math menu inside the matrix menu. So you go into matrix, and then there's names, math, edit. The math part is exclusive to matrix operations. And if you scroll all the way down to B, you'll see RREF. That stands for row reduced echelon form. So we hit enter. And then you go back to the matrix that you want to put in row reduced echelon form. For me, that's matrix A. And there you go. So we get 1, 0, 2, 0, 1, 1. Everybody okay with that? So the row reduced echelon form of this augmented matrix was 1, 0, 2, 0, 1, 1. Now remember what this stood for, what the columns and the rows in a matrix stood for. The columns stood for variables and the rows stood for equations, right? So what this is telling me is essentially that x plus 1x plus 0y is equal to 2. Or in other words, this is saying x is equal to 2 and y is equal to 1. And so the short version of this is that you can ask to put any augmented matrix in row reduced echelon form, and that if it has one solution will end up looking like this. If the system has one solution, it'll end up looking like this. And this system is equivalent to this one. Gauss-Jordan elimination is basically a system where you do elimination method on the equations, and then you replace equations with different equations, right? So you get a system of equations, that's identical to another, and you just kind of keep going through that. And there's a bunch of row operations that you can use, right? So if you have to do it by hand, it's a long process, but you just kind of keep going through these row operations until you get something that looks really, really nice. And that's your solution. That's your solution. Okay. By the way, you'll notice that row reduced echelon form has this nice effect with zeros and ones. Okay. What it tries to do is it tries to have a stair step effect where the ones are stepping sort of down to the right. Okay. And so ones are on a diagonal. If you get a one, also you want a zero above it. Okay. A one is a leading coefficient, you get a zero above it. Obviously, this one is also there, it's not leading, so that it doesn't have to have a 1, 0 above it. But this one's a leading, and therefore you put all zeros above it. And so there's this process, and this is where I was gonna get at. There's this process that's described in the book. I'm not gonna that talks about performing row operations on a matrix. That's what we're doing. That's the underlying. And you want the main diagonal to be ones. And then once you do that, you can actually make the numbers above these ones. So you make the numbers below 0 by elimination, basically. So once you eliminate this variable in that equation, this variable in that equation, then you eliminate this variable in that equation. Once you eliminate that, then you can make zeros above by going back and doing some eliminations there, eliminations here. That makes sense? So basically, you start by making everything 1, and then eliminate below, and then you eliminate above, make all those zeros. And there you go. And it shows you kind of how it's done. I'm not going to go through that because we can just RREF. Does that make sense? With our calculator. We can just ask our calculator to do it. All right. Now, the other thing that I want to mention is that we've been using X's and Y's this whole time. A lot of times when we get to systems of linear equations with matrices, instead of their variables being X's and Y's, the variables become X1s and X2s. All right. Just because eventually when you have lots and lots of variables, you run out of letters. And so with systems of linear equations, with matrices, instead of having X and Y and Z, maybe they'll have something like this: 3x1 plus 4x2 minus x3 equals 12. And then 2x1 minus 6x2 plus 7x3 equals 28. And then I'm just making these up. These are going to be ugly numbers, I'm sure. There you go. So instead of having X, Y, and Z, they have X1, X2, X3. Hopefully that's not a big deal. Should be fairly intuitive, I hope. So these are just subscripts rather than so what we do is if we want to solve this using Gauss-Jordan elimination, we're not going to actually do the process of elimination, but we will use an augmented matrix. All we're going to do is in our calculator, put in the augmented matrix. And put that into row reduced echelon form. The book always has these vertical lines, I leave them out. And so go ahead and grab your calculator in the matrix menu. If you wanna, I'm gonna do it in A. This is a 3x4 matrix. And then go into the math menu. By the way, you do have to go back to the home screen before you go to the math menu on the matrix, okay? So go back to the home screen. And then do RREF of whatever matrix. I put mine in A, but if you put yours in matrix B, that's fine too. And when I go and do that, oops, I ended up glare on my screen with this matrix, which is quite ugly, right? If you want this to have entries that are fractions instead of decimals, you can do that by just going into the math menu, the regular old math menu. So hit the math button and then say convert that matrix to entries which have fractions rather than decimals. And then that'll convert it to Does that make sense? So if you wanted it to have fractions instead of decimals, that's perfectly all right. Or decimals rather than fractions. I'll probably round things to a couple decimal places when I put it on the board though. All right, just because that's easier when I put my final answers on the board. Think about how long this would have probably taken with standard elimination. Remember, we did a 3 system with 3 variables example. With standard elimination, And even with, we had a really, really nice system, it took a while, right? Here, this is a very ugly system. And it goes pretty quick. It's a pretty quick process to solve. Let me oh, I forgot to say, you'll once again notice we have this nice diagonal ones and zeros elsewhere when you go RREF for this first little block, right? That's exactly what we wanted. And then, well, the 1306 over 191, negative 393 over 191. 54 over 191. Got a really ugly denominator there because of, I just made up the numbers, right? Which is what I have planned on. And that means x1 is equal to approximately 6.84. X2 is equal to approximately negative 2.06. And x3 is approximately positive 0.28. Positive 0.28. Okay. So that's the essence of Gauss-Jordan elimination. Again, row-reduced echelon form has this nice block when we have a one solution case. We have ones on the diagonal and then zeros elsewhere other than the equal to constant part. That's when we have the nice case. Does that make sense? Now let's take a look at another instance where we might not have a nice case. So I want you to try this on your own. Let's say we have 2x1 minus 3x2 is equal to 11. And then negative 4x1 plus 6x2 is equal to 23. Let's solve using the augmented matrix here. Or solve using Gauss-Jordan elimination. All right, good. So the augmented matrix is 2, -3, 11, -4, 6, 23. When you do Gauss-Jordan elimination, a strange thing happens. Oh, I think you get this. 1, -1.5, 0, 0, 0, 1. Now, this also has that same stair stepper effect where my leading terms in each row are 1. And then in each row, I have zeros before ones. If I look at the columns, I have this leading pivot position of 1, I have a 0 under it. Here's also a leading term of 1, I have a 0 above and below, technically. There's no below, but same thing here, I have a 0 above. But. So my leading terms of 1s have this stair stepper effect. Okay. But I had to step down and way across to get to the next one. Now, if you think about what this means, remember when we had this, I'm just gonna make up numbers. We had something like this. This meant that x1 is 5 and x2 is 7 because that's what the equation said. If you think about what this last equation says, this says 0x1 plus 0x2 is equal to 1. So the last line says 0 equals 1. We should recognize that 0 is not 1. All right? That's a false statement. So the system has no solution. Remember we were dealing with that through systems of linear equations, and we eliminated some, and we got a false statement. False statements meant no solution. And if you got a true statement like 0 equals 0, and then something else up here, that would have been infinitely many solutions. Okay. But if any row gives us a false statement, and the only way you get false statements with row reduced echelon form is if you had 0 equals 1 or 0 equals something else. But this system is one with no solution. So that's the other method. That's what it looks like to have no solution. That makes sense. There you go. Now, unless you want to do lots of stuff by hand, if you're willing to use technology, that's really all you need to know. Now we can convert into augmented matrices. We can have our calculator do all the tough work of putting it in row reduced echelon form. And then we can simply interpret that row reduced echelon form matrix into either a solution, that's what's going to happen most of the time, or something like this where there's no solution, or if we end up with a row that says 0 equals 0, that's probably infinitely many solutions. Any questions about that? We'll do some more of these in a little while. Using Gauss-Jordan elimination, using that reproduced echelon form. But for right now, I'm going to give you another option. We're going to do systems of linear equations via a matrix inverse. Okay. So in 9.5, we multiplied matrices. And we saw how to multiply matrices and all that kind of stuff. I want you to notice, and before we get into matrix inverse, you have to notice something. Let's say I have a 2x2 matrix. Let's say I have 2, 3, -4, 7. And I multiply that by this matrix. It kind of looks like my row-reduced echelon form matrix with augmented matrix without the equal to parts. So it just has diagonals of 1 and zeros elsewhere. So 1's on the diagonal, 0 is elsewhere. Well, if you multiply this matrix, 1, 0 times this one, 1, 0, 1 times 2 minus 4 times 0, or 1 times 3, 0 times 7. Notice what you're getting. You're getting the 2 and the 3 there. Because the 0, 1 times 2 is 2, 0 times -4 is 0. And then you go to the next one. 1 times 3 is 3, 0 times 7 is 0. So you just get 3. If you do this one, 0 times 2 plus 1 times -4, you get a -4. 0 times 3 plus 1 times 7 gives you 7. So you get this matrix back. By the way, I'm not going to go through all the multiplication, but if you would have put that matrix, this special, where we have 1's on the diagonal and 0's elsewhere, and you multiplied it on the right-hand side by 2, 3, -4, 7, it turns out you can do the same thing, and you'll get the same answer. You'll get the matrix back. This is not exclusive to 2x2 case, to the 2x2 case either. Let's say I have a 3x3 case. So we have 8, 6, -2, 7, 10, 9, -4, 0. Now, if you're guessing what's going to happen, what do you think is going to happen?
Something similar.
Something similar, right? So 1, 0, 0, When you multiply that, think about turning it up. The 1's gonna multiply the 8, and then 0's multiply the other 2. So you just get the 8 back. Then, when you move over, 1 multiplies by the 6, 0 multiplies by the other 2, so you just get the 6 back. Then you move over, -2 times 1 is -2. The 0's give you 0, you just get -2 back. So the point that I'm making is that first row multiplication gives you back 8, 6, -2. And then if you look at what happens on the second row, when I take this second row and multiply it, well, guess what's gonna happen? I'm just gonna get the second row of this matrix. The 1 is gonna multiply by 7, and then by 10, and then by 9, and then the 0's are gonna cancel out everything else. And then I'm gonna move on to the third row. And the 0's cancel out everything in here. So when you take the 1 times -4, you're gonna get the -4. 1 times 0, you get 0. 1 times 3, you get 3. And just like this one, if you'd have taken that matrix and multiplied that matrix where the 1's are on the diagonal and 0 elsewhere, on the right-hand side, you would have gotten the exact same thing. You would have gotten your matrix back. Okay. These matrices are called the identity matrices because under multiplication, they give you back the matrix you started with, right? So the identity matrices are matrices, I should say, are square matrices. Square meaning same number of rows as columns, right? 3 by 3 or 2 by 2. There's no 3 by 4 identity matrix, it has to be square. Our square matrices with 1's on the main diagonal and 0's elsewhere. The notation usually is just I, but sometimes it'll have a subscript, which tells you whether it's a 2 by 2 or a 3 by 3 or a 4 by 4 or whatever. So sometimes people just say I equals and then use another I for a different size. That's fine. Other times you'll see subscripts. I sub 2 means the 2 by 2 identity matrix. I by 3 means the 3 by 3 identity matrix. And they essentially behave like the number 1 does. 1 times anything is itself. The identity matrix times anything is itself, as long as the dimensions work out. All right? And we know that mathematically, dimensions have to work out. So if dimensions work, then if I take the identity matrix times any matrix, I get back the original matrix. And if you take the identity matrix, multiply it on the other side, if the dimensions work out, you get back your identity matrix. Sometimes one of these will work because the dimensions in one direction work out fine, but the dimensions in the other direction don't. So that's what I want to say. That's why I wrote them as two separate things. If A is square, then both dimensions work. Like we just had written on the board. All right, so that's the identity matrix. Now, the inverse matrix of matrix A is denoted A to the -1 power. Okay, when it exists, I'll put that. So if an inverse exists, it's going to be denoted by A, and the exponent's going to be -1. This has the property that A times its inverse is going to be equal to the identity matrix. And if you take A inverse times A, it also is the identity matrix. By the way, if both multiplications have to exist, then what's that mean about the identity matrix? Well, it's only going to work. Or excuse me, let me rephrase this. I messed that up. If it works both ways, if the multiplications work both ways, then you can argue that A has to be squared for this even to make sense. Because if you have 2 by 3, this would have to be a 3 by something to make it. And so the short of it is inverse matrices will sometimes exist and sometimes not. I should say inverse matrices only exist, will only exist for some square matrices. I was going to say will exist for will only exist for some square matrices, but it's all the same, no big deal. Okay. Now, how do you find an inverse matrix? Well, there is a way to do it through Gauss-Jordan elimination. All right. It turns out that if you put your matrix in, let's say it's 2 by 2, and then you put the identity behind it. Okay. I'll show you two methods, and then I'll show you the one I like best second. Does that make sense? All right. All right, so let's say to find an A inverse given A. Right? Let's say A is 5, 9, 2, 4. Method 1 is to go RREF of this matrix. I take basically my A, and I put it into the left two columns of a matrix, and then in the right two columns, I put the identity matrix entries. Now I'm gonna grab my calculator and do this because I don't want to spend a lot of, I'll do this matrix A again. So what's that, 2 by 4? Zero, 2, 4, 0. So I'm trying to do this quickly, because again, this is not my favorite method of doing this. What you'll get, hopefully, is the identity matrix now in the first two columns. And then in the second two columns, you'll get this other thing. This means that the inverse matrix of matrix A is 2, negative 4.5, negative 1, 2.5. And if you go through the multiplication and you check A times A inverse, you'll see that you do get the identity back. Sounds crazy, huh? Now, that's not the way I like to do that the most. Not my preferred way. My preferred way is that if I have A, all I have to do is type A to the negative 1 power in the calculator. As long as I have a TI-83 or something else that's fine with matrices. Okay. And that's just going to give you back the inverse of A. So you can see this is what I just did, the row reduced echelon form version. Okay, now let me go change my matrix. Let's change it just to the normal A. 5924. 4. Quit. And then what you do is you go back and recall matrix A. And then I like using this button here, the inverse button. I think you can also do caret -1 too, that's fine. But I like using the inverse button. And sure enough, that gives me back my inverse. So we can find the inverse matrix just by doing that. Okay. And I'll show you in just a second. Well, I can show you right now, I guess. Let's do the following on my calculator. I'm going to take matrix B this time. And let's just take a 2 by 3. Type in any 2 by 3 that you want. Okay? Type in any 2 by 3 matrix that you want to see. Then go back to the home screen. And if you type in B inverse in your home screen, it'll say that's an invalid dimension, right? Because our inverse, to get an inverse, the matrix has to be square. We okay with that? So to get an inverse, the matrix has to be square. Does that mean all square matrices are going to have inverses? No, some matrices do not have inverses. Most square matrices do, but there are going to be occasions in which you have a square matrix which does not have an inverse. And let me show you one real quick. Just for an example. So let's do a square matrix. And I want you to type in 1, 2, and then type in 2, 4. Okay, that's a square matrix. If you go to your home screen and then bring up that square matrix, if I just hit enter, that's fine. If I say, give me the inverse of that B, it's going to say error. Notice that's a different error. In the first one, since it was 2 by 3, it said dimensions mismatch, or dimensions are wrong, or incorrect dimensions. I can't remember the phrasing, but it was something about the dimensions being wrong. This time, it says error singular matrix. All right. So if I have a B, which is 1, 2, and then 2, 4. I screwed that up. I forgot to write that down. Sorry. So over here it was 2. B inverse does not exist. I think if there's something that doesn't exist, then you write NS in the whole thing. And all the entries, you know what I'm saying? So for no solution. But B inverse does not exist. And the fancy word for having a square matrix, which doesn't have an inverse, is called a singular matrix, right? A square matrix that does not have an inverse is called a singular matrix. So that's why the thing says singular matrix. And obviously, if it has an inverse, then it's called non-singular. All right. If singular means it has no one, does not have an inverse. But if you want to find an inverse, again, there's no ways to do it, but the quickest way is just use your calculator. A inverse button. That's quick. Now here's where inverses will help us with a system of linear equations. All right. So what we're going to do is we're going to look at a system of linear equations and create a single matrix equation. That means the same thing. Here's how we do that. Let's say I have 3x1 plus 4x2 equaling, oh, what do I want? I guess 18. And then I have x1 minus 7x2 equaling negative 19. Fair at that? Trying to get one that works out well. So this system can convert into a matrix equation. I'm going to take 3, 4, 1, -7. Notice that is just the coefficients of my x1s and x2s. And then I'm going to multiply times the matrix x1, x2. And I'm going to set that equal to the matrix 18, -19. I want you to notice that that these two things are the same, all right? Because what you would do is you would take this 3, 4, and you multiply it times x1, x2 to get 18 as your first entry. You see that? Take the 3, 4. When I multiply it, I have to turn it vertical and multiply it here. So I get 3 times x1 plus 4 times x2 is equal to 18 for that first entry multiplication. That's exactly what my first line is. And then 1 x1 minus 7x2 is equal to -19. That's exactly what my second entry is. Now let's call this A. Can I call that A? Everybody good? So we have A times x1, x2 is equal to 18, -19. Now, I know that A has an inverse. It does, you can just check if you want to, but I know that A has an inverse, I set it up that way. What if I multiply the inverse of A on both the left and the right-hand side? If I take A inverse and I multiply it on the left-hand side, and then I take A inverse and I multiply it on the right-hand side, multiplying both sides of an equation doesn't change the solutions, even in matrix equations. I multiply, it's kind of like multiplying both sides by 2, right, in our standard equation. As long as the inverse exists, I can do that. Now, what happens over here? A inverse times A times this matrix. Remember we said matrix multiplication is associative? So I can do the A inverse times A and get the identity. So what's that mean? It means that I can solve this matrix equation by simply taking A inverse times 18, 19, -19, excuse me. Everybody see why that is? Identity times anything is itself, so I can just say identity times anything is itself, so I get this back. So if I'm willing to use a matrix equation, I can solve a system of linear equations just by using the inverse times this. So let's go ahead and do that in this case. Now, I'm gonna write my matrix A into my calculator. 3, 4, 1, -7. Oh, I'll show you here. Okay, all right, good. So I plugged in matrix A into my calculator. Okay, now the other matrix that I'm going to use is B. That's going to be the matrix for the constants, all right? By the way, that's also the traditional symbolism, okay? Is B. We use B for the constants, A for the coefficients. The constants are 2 by 1. Some people call this matrix a vector matrix because it just has a single column. Or vectors have a bunch of entries, but and we had what, 18, -19 for B. And so with what I know now, I can go back to the home screen and say, let's take matrix A, find the inverse of that, and then times it by matrix B. By the way, that's not the same A, so use people there. Way to get that. I hit enter and I get 2, 3. So first off, everybody understand how they're typing into your calculator? Just type in the coefficient. This is called the coefficient matrix, the one I'm using now, as opposed to the augmented matrix. The augmented matrix, like we use with Gauss-Jordan elimination, had the constants in there. The coefficient matrix just records the coefficients, right? So I got my constant matrix B, my coefficient matrix A, and I take A inverse times B, and it gives me 2, 3, which is exactly what I want. That's my solution. What we said here is this is 2, 3, so that means x1, x2 is equal to the matrix 2, 3. Sometimes people call that the vector matrix 2, 3. That means x1 is 2 and x2 is 3. Now, once you've seen that once, you can say in general, if we have a matrix equation and A inverse exists, then I can do A times X. Usually when we say X here, They bold it, sometimes we put a capital X. X is just a variable matrix. Multiply A inverse on both sides, and you get that. Obviously, this works only when A inverse exists. If A inverse doesn't exist and you try to do this, it'll say error singular matrix. And then you say, oh, this you can't solve using this method. And by the way, a singular matrix also means either you're in the no solution or infinite remaining solution cases. I'm not going to give you a lot of those, but that's just what it is. If you read along in the book, they use a bold X instead of a capital X, and a bold lowercase b instead of a capital B. But writing out on the board, it's easier just to say capitals so people see that they're going to be matrices. Does that make sense? So there might be a slight difference in notation, but this is the idea. So here's what I want you to do. I want you to do a solving of a system of linear equations. Let's take 4x1 minus x2 equals 13, and 5x1 plus 7x2 equals 84. So I want you to solve that system using the inverse matrix equation. So using the matrix equation, solve that system. All right, so let's set these up. We go 4, -1, 5, 7 times the x1, x2 matrix set equal to 1384. And basically, if we call this A, I don't like to overly write things. I can simply take A inverse, multiply it on both sides. Whatever that happens to be in our calculator. I haven't done the math yet, sorry, I forgot to do that. Forgot to put it into the calculator. -1. So. I ended up, well, depending on whether you write fractions or decimals, it doesn't matter. I guess I'll write both. x1, x2 equals 175 over 33 and 271 over 33. Which rounded to a couple of decimal places, which you would have to do. It'd be like 5.30 and 8.21, is that right? Did I do that correctly? Good, all right, making sure. Sometimes, especially when I'm going quick and I'm writing stuff down quick, it's easy to get one number wrong and then that'll throw the whole thing off, obviously. Now, the two examples I just did were both 2x2 matrices. For the coefficient matrix. You could have also had 3 equations with 3 variables and done the exact same thing. Or 4 equations with 4 variables and done with the exact same thing. As long as the inverse exists, you can solve it this way. And if the inverse doesn't exist, you're going to find out at this step because it's going to say, hey, there's an error here. That's a singular matrix. And then you can't do it. And then you'll know you're either in the no solutions case or the infinitely many solutions case. All right. Any questions about this? No. This is a lot quicker than doing the methods we looked at in 9.1. Hopefully it is. Hopefully it is. When you get to use technology to do stuff, and that really can lighten the load. And so that's one of the reasons that I put 9.1 homework due this week instead of last week, right? We were done with 9.1 homework last week, but now if you want, you can say all that elimination, substitution method stuff, we can go a little bit quicker through this. So let's go back to 9.1. Back to section 9.1 and take a look at some of the problems that we had skipped. In particular, we had skipped some word problems. All right. And essentially, this is going to be, I'm going to look at some of the word problems, and I'm just going to set them up. And instead of using elimination or substitution, I'm going to use the methods we learned today. All right. Either row reduced echelon form or inverse matrix. So we're going to solve some word problems. And we're just going to kind of go through various problems. Let's take a look at problem 61 on, this is in section 9.1 if you're not following along. It says find two numbers whose sum so sum is 28 and difference is 13. So find two numbers whose sum is 28, whose difference is 13. We're going to call the things that we're going to find, I'll call them X and Y. You could have called it X1 and X2. Could have called one, and the other M. Whatever variables you like, that's fine. I'm going to call it X and Y, though. Is that right? So, X and Y are my numbers. If their sum is 28, that means when you add them up, you get 28. And if their difference is 13, that means when you subtract them, you get 13. Now here, the way I've subtracted, I've assumed X is the bigger one. And so there you go. So that creates a system of linear equations. This one's actually pretty easy to solve by hand if you want. But we just learned our new techniques, so we might as well use them. Let's use the RREF method. So my first line in my augmented matrix, going to be a 2x3 augmented matrix, is 1, 1, 28. My second line is going to be 1, -1, 13. Then I'm going to go back, row reduced echelon form that. So X would have to been 20.5 and Y would have to have been 7.5. Right? Even if it's not quicker, it does certainly feel quicker, doesn't it? Again, the one thing you have to be watching out for every time when you use your calculator is that you hit all the buttons correctly, because one little mistake can throw the whole thing off, right? So if you throw in a different augmented matrix, if I typed in 25 instead of 28, then everything's messed up. But so other than that, fairly nice to deal with. Let's look at another in this example. All right, another in this section. Another example in this section. Ooh. Let's see. That's not very interesting. Let's look at number 66. All right. Can we read that here, by the way? If I can zoom in a little bit. There we go. So 66 says there are 276 students enrolled in a class. Chemistry class. 5 times the number of students passed as failed. Find the number of students who passed. And the number of students who failed. Number of students. Where is that? Now I'm going to use P for passed and F for failed. You want to use X and Y for something, that's fine. Whatever letters you like. But that'll be easy. P is for passed. F is for failed. So since there were 276 students in the class, that means combined the passed and the failed together added to 276. Now, the second sentence is a little bit tricky. 5 times the number of students who pass, 5 times the number of students pass than fail. All right. Now, when you read that, Was there more students who passed or more students who failed?
More students who pass.
Passed, exactly, perfect. So more students who passed, that's all. So the number of students who passed is gonna be 5 times the number of students who failed. Now, if we were back in 9-1, we'd use substitution. And then solve and that kind of stuff. If you want to use the stuff we use today, you're gonna have to make sure we line things up. So we're gonna have to convert this system. The first equation doesn't need anything, but I'd have to subtract 5f from both sides. If I were to do the things we're doing today. Does that make sense? And once I have that, then I'll once again use the row reduced echelon form version. I can do row reduced echelon form 1, 1, 276, 1, -5, 0. And what I got, that the row reduced echelon form of the matrix is 1, 0, 2, 30, 0, 1, 46. And that means 230 students passed. And 46 students failed. Any questions about that? Now, you can probably tell that I tend to use RREF more than I use the inverses. Set up the matrix equation. That's just me. There's a couple of reasons for that. Mostly it's because the RREF will tell you if you have infinitely many solutions or no solutions. The inverse method, if you get into one of those which has no solutions or infinitely, you can't really tell which one it is until you go through it. So I tend to use RREF rather than the inverse, but if you like inverse matrix better, that's fine. Whichever way you're doing that though, notice our original system, we have to have things all lined up if we want to use matrices. Okay, we have to have our variables lined up in columns, our equal signs lined up, and our constants lined up. If we want to use either the RREF, Gauss-Jordan elimination, or the inverse matrix using matrix equations. Okay. Any questions? Great. Let's do a mixture problem. Let's do number 69 here. So this is a very classic type problem where a mixture of solutions is being mixed to get a different solution. So this says a scientist mixes a 10% with a 60% solution to get 25 gallons of a 40% solution. How many gallons of each original solution was mixed? How many gallons of each were mixed? So a very, very classic mixture type problem. All right. There we go. So we got a mixture of something. And we need to find out what's the two original mixes. Now, we gotta call one of these a variable, the 10%, and however much of the 10%, we gotta call that a variable. How much of the 60%, we gotta call that a variable. Doesn't matter which letters you use. I'll use X and Y's. If you prefer A and B's, use A and B's. I'll say that X is gonna represent the amount of the 10%, and Y represents the amount of the 60% solution. Now, on all of these type of mixture problems, we're gonna have two equations. One is the total amount. So how much of each? Let me state this a different way. When you add them together, since I know together they make 25 gallons, my first equation is just the amount equation. My second equation is going to be the percentage equation, or how much saline is in this. It was saline, right? Okay, saline. If it was acid, it'd be acid. If it was saline, it's saline. No big deal. But this is saline. So, of the amount we add of the 10%, if I take 10% of X, that's going to be how much saline is in the X part. If I take 60% of Y, that's how much saline is going to be in the Y part. The amount of saline in the total is 40%. 40% of what? Well, 40% of the 25 gallons. So my system of equations is just that. Now I'm gonna write this a little bit nicer, not that much nicer, just 0.4 times 25. I don't know what that is off the top of my head, so I'm gonna type it in. That's 10. And then I say, well, now let's solve it. By doing the RREF of my augmented matrix. Again, this is a 2x3. And when I did the RREF, I got this 1, 0, 10, 0, 1, 15. That means I needed to add 10 gallons of the 10% and 15 gallons of the 60%. That makes sense. Any questions about that? Pretty straightforward, not bad. Okay. These are kind of classical mixture problems. And by the way, you can mix things like saline. You can also mix things like money. There's an example in the book that talks about money invested into an account. Let's take a look at, for instance, 72. Investor invests a total of $25,000. The last one here. Into two bonds. One bond pays 3% interest, and the other pays 2 7/8% interest. The investor earned $735.50. How much was invested in each account? Is that right? All right. Good. Everybody get the need. Okay. So I'm going to use X and Y again. You can use whatever letters you want. X is the amount in the 3% account, and Y is going to be the amount in the 2 7/8. Now, I would rather see that as a decimal 0.875. Is that okay? So, okay, 2 7/8 is 2.875. That way, when I write it in my equation, I can convert to decimal line. Convert from percentage to rate, easier. Well, it's basically the same setup. The amount invested in both accounts has to be equal to the 25,000 total. And then if we do 3% into X, when I convert that to a rate, it's going to be 0.03. And when I convert the 2.875 into a rate, it's 0.02875. That's the amount of interest they gained. And we know that that has to be equal to the 337.50. I said that wrong. 737.50. Again, it's kind of an ugly, we gotta have ugly coefficients. So if you are using elimination, it's not terrible. You can use elimination to do, just faster using these matrices. So the RREF matrix is going to be 1, 1, 25,000. 0.03, 0.02875, 737.50. Oh, I got that again. Huh. I got nice numbers again. See, book problems often come out with nice whole number answers. Don't think you're always going to get nice whole number answers with, excuse me, on all the homework problems, right? You might get something like 12,870, and then sometimes. But the investor must have put 15,000 into the 3% bond and must have put 10,000 into the 2.875 or 2.78% bond. That's what it's telling you. Then okay, I don't have to put x equals 15,000, y equals 10,000. Kind of skip that step, but. This word problem stuff pretty straightforward. So create two equations with variables in them, two linear equations. And then if you wanted to, you can use substitution or elimination, that's fine. But now that we have these calculator methods of doing the RREF or using the inverse, makes our life a little bit easier. Okay. Any questions about that? Well, that is all of the material for chapter 9. You should be able to do all of the homeworks for chapter 9. And now, if you want to go back to 9.1, check your answers. You can check your answers in fairly quick and efficient manner. Okay. Excuse me. There. All right, so that's chapter 9. Now, in chapter 10, what we're going to cover on chapter 10 is going to be I have this in the wrong order. Weird. So what we're going to do is we're going to cover conic sections. All right. So chapter 10, going to cover conic sections. There's going to be 3 conic sections. Well, 4 really that we're looking at. And then we're going to shift those conic sections. That's going to sound weird, but basically we're going to look at the conic sections who's centered at 0, 0, and then say, well, if we want to, we can translate those and put the center in any other place if I like. So, weirdly enough, chapter 10 covers conic sections. The ellipse comes first in 10.1, hyperbola, and then we do parabola, and then the circle is a special version of the ellipse. And then we translate them. That's 10.1, 10.2, 10.3, 10.4. Okay. But it doesn't do general of what's conic section beforehand. So that's what I kind of want to do today. All right. So I want to talk about what is a conic section before we get into 10.1. Now, the short answer is it is what you get by the intersection of a plane and a cone. When we take the intersection of a cone with a plane. Now, when I say cone, I don't mean obviously an ice cream cone, but that's what you should probably think of, right? Think of an ice cream cone, a waffle cone. But in general mathematics, we have to go forever. Ooh, I didn't draw that very well. So draw a big X. Okay. So when we say a cone, we're thinking of it in mathematics, this type of cone. And this type of cone is going forever up and forever down. And we're going to take a plane and intersect that. Now, by plane, I mean a standard Cartesian coordinate XY axis. Okay. And I'm going to slice this. And I can't, this is not a very good plane because it's flimsy, but I'm going to slice this in some direction. Right? So imagine my plane is coming straight out of the board. I can slice it into here, 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 all types of those types of intersections. Now, if the plane slices right at this point, so if the plane, I'm going to try to fold this so I get more stable. If my plane slices it right at that point, right here, okay, that's what we call a trivial conic section because I only get a point, or if you kind of rotate the plane a little bit, you might line up exactly with a line, and so you get a line, all right? Or if you sliced it like this, you technically get two lines. You get this line and this one. That makes sense? So that's called a trivial slice. So those aren't very interesting. Those are lines or two lines or a point. What's more interesting is when we slice it away from this point. So if I take it and I slice here, or if I slice here, or if I slice here, or if I slice here, okay? I'll do some different, quote, slicing. If my slice is here, my slice is horizontal. Then I get a circle. So on the plane, you would see a perfectly, just see a circle. If it wasn't perfectly horizontal, but it's a little skewed, then what would happen is that circle would have been a little bit stretched out. And that's an ellipse. So if the slice goes through like that, that gives an ellipse. And And this one I've stretched out more more horizontally than vertically, but you could also stretch out more vertically than horizontally, depending on how your plane looks. If, when you slice, you slice in a way that is exactly parallel with this line or with this other one, but let's just say this line. So I slice parallel, that gives a parabola. We've seen parabolas before. And then lastly, if you slice in a way that goes through both sides of the cone, I didn't do that justice, but with my drawing. But if I do something like this, then that's what gives the hyperbola. All right. By the way, a hyperbola, we'll see, is not two parabolas. Okay? They're very, very different. Okay. A hyperbola does not have a parabolic shape, except like where it turns. Where it turns, it kind of looks parabolic. But if you scroll out, and again, we'll see this later, does not look anything near what a parabola looks like. Right? When you scroll out. All right, so that's what a conic section is geometrically. Algebraically, a conic section can be written as a quadratic in two variables. As a, I'm just going to say second degree. Polynomial. Two variables. I don't want you to get thinking it's going to be a parabola. So second degree, so you can have an x squared. You can have actually the x being multiplied by the y. You can have a y squared. You can have an x. You can have a y. You can have a constant. And if you combine like terms, looks like that. You can always force it to look like that. So the highest degree of any term is 2, and we have 2 variables. One is x, one is y. Do you get that? So geometrically, all of these intersections are going to look like that. Now, like I said earlier, we are going to, in our class, ignore the trivial ones. The trivial ones are where we have a point or a line or 2 lines. And the trivial ones algebraically are going to have 0 for A, B, and C. And so it's just going to be like a line. Does that make sense? So algebraically, the trivial ones don't have any quadratic pieces, don't have any second degrees. The circle, the ellipse, the hyperbola, and the parabola, those will all have terms where we have a y squared, or we have an x squared, or we have an x times y. That makes sense? And we'll start out with nice versions, ones where we don't have any xy's, we don't have any interaction terms. Any questions about that so far? Good. So you're going to see quadratic pieces. You're going to see an x squared, you're going to see a y squared in the ones we're dealing with. All right. Okay. Well, that's what we'll do next time. So for next time, we're gonna, now that we know this, what a conic section is in general, it's how, what you get when you slice the cone with a plane. And remember, what I'm saying, an infinite cone. These are goes forever in both directions. You slice cone with a plane, the intersection of that is going to be a conic section. We're going to focus on these 4 non-trivial ones. All right? And we will see how that stuff works next time. Okay? All right. I'll see you next class. That's Wednesday. And then we'll cover all the conic section stuff. All right? All right. See you then.